And we're live. All right. Thank you so much, everyone, for being here today at the first trial lesson for AI Foundations. Naveed and I have been really excited, and we've been working on this for a little while. I'll just introduce myself. So my name is James, and I've been teaching coding on YouTube for a while. And yeah, a couple years ago, I got into AI, and Naveed was like, I found him as like the perfect teacher. So yeah, I'll let you introduce yourself, Naveed.
Yeah, hello everyone. I'm Naveed from Pakistan. I'm basically an electrical engineer and an ML researcher. I've been working in ML for the past 4 to 5 years. Um, ML is something that I utilize in my own research, but also I've been working with clients from all over the globe. I've also been teaching machine learning on different platforms, and I'm here to teach you people machine learning. So I'm looking forward to it.
Okay, cool. Yeah. Z, can you introduce yourself? And then after that, Victor and Burhan.
Hi everyone. My background is in like biochemistry and genetics, and then I recently did a master's in bioinformatics, and I'm interested in applying sort of machine learning, language models, etc., to like problems in biology. So yeah, I'm excited to be here.
Sweet.
Hello,
Victor.
everyone. So,
Oh,
no, yes, sure, Victor, go on.
anyone.
Hello everyone. I'm Victor. I have a background in computer science, still studying computer science. This is my third year computer science student, and I'm interested in like finding like applications across the board about using AI, learning more in depth about how AI works.
Hello, everyone. Myself, Burhan. I just finished my first year. I'm studying computer science as my major, and I'm currently exploring ML during my summer vacations. And I thought this would be a good opportunity for me to explore this side. So yeah.
Cool. Awesome. We have also a couple of people in the comments as well, or who are just watching. So if you have any questions or thoughts, feel free to introduce yourself as we're moving along. So yeah, let me just tell you for a few minutes about like what it is that we're even doing here, and then after that, yeah, Naveed will get started with today's lesson. But so yeah, what is this that we're doing? Um, basically, um, I met Naveed a couple of years ago when I was actually looking for a teacher online to teach me machine learning. And yeah, I found this guy, and I started learning so much, just one topic after the next. And yeah, we got along pretty well. And actually, I even managed to teach him a couple of things too, I think, about software. And we just kept
Yeah,
talking. We just kept talking, and we started making some videos together. And then we thought, oh, it would be really cool to do sort of like a course together. Um, I I think we'll probably interrupt each other sometimes, but I think that's sort of like the whole idea of this. Like, the more interruptions and the more discussion, then this will be even better. Um, so yeah, we want to just create not like a traditional like lecture format, but really like discussions where we can just like debate stuff and really just talk about the stuff that we don't understand. Um, that's why learning from Naveed has been so useful for me. And the format right now is probably just going to be like 2 sessions a week. We'll see about the scheduling, and then really small mini projects that come with like collab notebooks. And then we're also going to have a probably a group chat. So anything else that I had to say about that? It's probably like an hour and a half long. And the first part of the session, like Naveed will go through the theory, and then after that, I will go through everything in Python again, the practical side of things. this is what we have lined up. It might change, but like just like starting out with intro to ML, regression, k-means clustering, neural networks, CNNs, and transformers. But we really just picked out some stuff that seemed, some of the more monumental models, but it's really impossible to to get everything important in a 5-week course. So yeah, we're gonna officially fix everything tomorrow, like who's in the program. But I think everyone here is definitely gonna be in it. And then the schedule, as far as the schedule, like it will be probably around this time, and then probably 2 days every week. So probably maybe like Thursday and Tuesday, but we'll fix that tomorrow as well. And yeah, that's everything that I can think of. Naveed, did you have anything else to throw in about this?
Yeah, so actually the goal here is to kind of make it as informal as possible. Just like you said, I'd love to hear your questions. I'd love to get interrupted. I'd love to have deeper discussions about whatever that might trouble you. So feel free to, interrupt me anywhere. I'd be doing the theory side, which could be a little bit boring, but I'll try to make it as pleasant as possible for you people. And then James would be walking you through the collabs, the notebooks that we have prepared. But I think we'll try to do our best, but if you genuinely want to learn, you'll have to get your hands dirty after the sessions, do the stuff yourself, take the code, apply it to different problems. There are tons of data sets online. So your effort would make the real difference. So yeah.
Cool. Yeah, and if you feel like it's an awkward moment to ask a question, you can also just type in the chat, just like question, and then we'll stop. Because sometimes it's awkward to interrupt on a call. But did anyone else have any questions? Cool. Well, then with that, I will let Naveed take it away.
Okay, so what I'll try to do here is kind of provide you a broader level picture of machine learning, and then I'll walk you through what is a typical workflow of a machine learning problem. The workflow kind of is different slightly for different problems, but majority of it stays the same. So I'll introduce you into that. I'll talk a little bit about the Python packages that are used. And if we still have time and everyone is present, we can then start talking about linear regression. So with that, let me present my screen. You see the whiteboard?
Yeah.
Okay, so broadly, machine learning can be categorized into 3 different categories. So one of it is called supervised learning. I'll write short terms for it because it takes time to write the full words, but I'll pronounce them as I write. Second one is unsupervised learning. And then we have reinforcement learning. So although recent developments in machine learning has been in what is called the generative machine learning or generative models, but I think since it's a basic level introduction, we'll stick with these, but I'll tell you where those models can fit in as we proceed. So supervised learning is further divided into 2 main types. One is called regression, and the second one is called classification. So in regression, the basic task is to predict a continuous variable. First of all, supervised learning is the branch where we have where the data comes. So this division is basically based upon what is the type or what is the form of the data that is available to us, because ML is learning from data. So In supervised learning, usually the data comes in input-output pairs, which can be considered as question answers. So you have an input usually represented by X, and you have an output represented by Y. And because we have this question answer pairs, the goal here is to devise a model, a technique which would learn that mapping between input and output. Why do we do that? Because if we once learn the mapping between input and output, we can then make use of the model to do prediction for something that we only have the input for, but we don't have the output for. So a typical example would be, suppose we have multiple images corresponding to different categories. So for instance, we have images for cats and images for dogs. And we know there's an image, and it's an image of a cat, and then we have another image, which is an image of a dog. The goal is to learn this mapping between this image and the cat. Now, one thing that comes to mind is there a direct way of doing this? Can we write some program that would somehow hard code this stuff? I mean, relating these pixels to this label. Well, it turns out it's a very difficult problem, because you cannot do that for the reasons that if you have a cat, a picture of a cat, as we know, computers store images in the form of matrix arrays, which are nothing but a bunch of pixel values. And there's like no way you can write or hard code what a cat looks like by just describing the pixels. And even if you do it, you can do it just for a single image. But when there's variations in the images, if the cat is sitting in a different pose, or if it's under different lighting or stuff, you'd have to write the whole program again to do that. So that's why we don't go through the usual way of doing stuff as we do using a computer. So traditionally what we do is that we write a program in order to solve something using a computer. We provide it in an input, and then it produces an output. But that rule is fixed. We have hard-coded it. So a typical example would be, we have an input, let's say X. X is nothing but just numbers. If I put in a number of 2, let's say, as an input, the rule that I have described, hard-coded here, is, let's say, it's squaring whatever comes as an input. So this is the rule. And then the output is whatever this rule is doing to that data. So if the input is 2, 2 gets squared, produces 4. That's how traditionally people used to solve stuff using computer. You have fixed, or you have hard-coded this rule. But just like I said, you cannot do this thing for a task like this, where you have a picture and you want to describe what is that picture of. So you cannot hard-code this thing. So machine learning pioneers came up with a different way of doing this. So they said that, what if we provided just the input and output from some historical data, and we let this computer decide for itself what rule it should be assigning, such that it relates this input to this output. So now what we do is we take the same computer, but now we provide it an input, and we also provide it a corresponding output. And now we task this computer program, to learn the mapping between this input and output. And once it learns that input and output mapping, the next time we can then take the same program, and we can just provide it in an input X, and it would be able to produce an output for us. So that's the whole idea of machine learning. Particularly what I was talking about here can be categorized as supervised learning, but even in unsupervised learning or in reinforcement learning, it's the same problem but presented a little bit differently. So if you have any questions, I'd love to answer them. I'll keep you reminding this over and over again, because I know sometimes it could be tough to ask questions, but I'll remind you this over and over again. So anyways, what I was talking here was, in supervised learning, we have this input-output pairs, and the goal is to learn the mapping between input and output. Now, supervised learning is further categorized into 2 categories. One is regression, and second one is classification. So in regression, the task is to predict a continuous variable. So it could be, let's say, the temperature tomorrow. Well, temperature can take on any values, so it's a continuous variable. So in regression, the goal is to predict a continuous variable. Or another example would be based on some input features, let's say the area of a house. the number of rooms and other stuff, and predicting what is going to be the price of that house. So now price can take on any values. It's a continuous variable, and there are number of values that it can take on. That's what we do in regression. In classification, we do the same prediction based on some inputs, but the output in this case is discrete. So it comes from certain predefined categories and not a continuous variable. So the example that I presented here, cat source dogs classifier, it is a typical example of classification where you have the input is an image, X, and the output is a label, either cat or a dog. But as you can see, it cannot take any values. It has to come from these two categories. Either it could be a cat or a dog. So that's what a classification task is handling. Now, the second category is unsupervised learning. So in unsupervised learning, just like I said in the beginning, this division is based on how the data is presented to the model. So in unsupervised learning, we don't have the data available as nicely paired input-output pairs. What we have is just a bunch of data, and we have lots and lots of amounts of them, and we want to derive some value from it. So what we can do in unsupervised learning is that we can take that data, and the first task that we can do is called clustering, so we can spot some clusters among the data. So by cluster, what I mean is we are looking for similar looking things together. So suppose the data that we have is just a bunch of pictures that we have, lots of pictures we have, but we don't know what those pictures are of because it's not, we don't have a label for it. But what we can do is we can maybe spot some clusters that these two images are looking similar, and maybe these two are looking similar. And this is what a typical clustering problem is solving. It's looking for similar looking things together. Now, this is an example of pictures, but you can consider this example also in terms of text, where you have a bunch of news articles, and the goal is to cluster articles which is about a similar event or similar topic. So that's one thing that we can do in unsupervised learning, which is clustering. The second thing that we can do is called dimensionality reduction. So although this is a little bit involved, but the simple idea is sometimes we have data, we have lots and lots of features, but not all of the features are important. And because if you have lots of features with the data and not all of them are important, and you are trying to do some machine learning on it, it would be very computationally heavy because all the features has to be taken into account. And even though not all are paying equal contribution to the output, or it's now having an impact on the output, still you'd have to take care of it. So in dimensionality reduction, the goal is to reduce those dimensions. So suppose you have an input data with 100 dimensions, the goal is to maybe reduce it to 50 dimensions, but do it in such a way that the majority of the information is preserved. So it's not like you are just randomly throwing 50 features from it. You'd have to do it in such a way that the information is preserved and you are just throwing away the least important features. So of course, it's not a magic. There are mathematical tools to do that. One of the mathematical tool that is used for this task is called PCA, Principal Component Analysis, but we'll dig deeper into it maybe later on.
Could you give like,
uh-huh.
When we're talking about dimensionality reduction, are we talking about like features that we can easily understand? You know, like would turning length and width into area be dimensionality reduction, or would that be feature engineering? Would that be different?
Yeah, so I think that would be more like a feature engineering, and that is more of like a handcrafted feature engineering because you are using your own concepts of combining two features together. Dimensionality reduction is doing something that is not like you wouldn't know that these two features that it has combined, it has taken area, it has taken length and width and combined it into an area. So that visibility is lost. The features that you get as an output, you wouldn't recognize what they represent. So that's one of the downside of it, that although you reduce the number of dimensions, but now these features are completely alien to you. So you don't know what it is. You can do speculations that maybe it's combining length and width into area, but that information is lost. So it's doing it in a way which is not really understandable. It's using concepts from linear algebra. The math is heavy, but yeah. So that's
so it's compression.
Kind of compression, yeah, you can describe it that way. And PCA is one way of doing it, but of course, you can also use a neural network to do that. The algorithms that are used for this task are called autoencoders. So
Got
you
it.
take the input, you squeeze it into a latent space of a reduced number of dimensions. You can use those as an input. So there are multiple ways to do it, but usually in the beginning, people, like majority of the time, they use PCA. Okay, so the third branch of machine learning is reinforcement learning. So it takes a little bit different approach from what the first two were doing. So they were making use of the available data to do interesting stuff on it. But reinforcement learning, what it does is that in this scenario, you have what is called an agent, and then you have an environment. And this agent, you place it in this environment, you define certain actions for this agent, what it can do, and then based on what it can do, you provide it what is called a feedback or a reward. So if this agent is doing something useful or desirable, you provide it a positive reward. And if it is doing something that is undesirable, you provide it a negative reward. And by steering the agent in this way, by providing this constant feedback, this agent over time learns to produce the desired behavior. So a classic example would be a car where the goal is to drive the car on a road without crashing it with the wall or something. So if the car is driving itself on the road correctly, you are providing it a positive reward. But if it does something funny, like crashing into the wall, you provide a negative reward. And by providing it this constant feedback, the car would over time learn how to drive itself. Now, of course, self-driving car is not that simple, but this is just an example of what reinforcement learning can do. So yeah, this is the broader categories of machine learning. Now, again, as I said, one hot topic these days is generative machine learning. So it combines concepts sometimes from some of these categories, but sometimes from all of them. For instance, if we talk about the LLMs, what they do is initially what they do is called, can be categorized into unsupervised learning, because in the initial stage, the way you train an LLM algorithm, which is usually a transformer, is that you have a bunch of text, a paragraph of text, and then you go just normally mask some of the words from that text at random, and then you task that algorithm to predict the next word, what comes next. So this is not supervised learning in the traditional sense, where you have an input-output pairs, where these labels are usually coming from human labelers, or they are obvious. In this type of learning, you are kind of just randomly removing some words from it. So that's why they have given it a unique name of called self-supervised learning, SSL for short. So that's one thing that it does. But then to make it a full-fledged chatbot, the second stage of it is then to train it in supervised learning fashion, where you provide input-output pairs. So you pose a question, and there's a corresponding answer to it. So initially, it was trained in self-supervised learning fashion, but then you fine-tune it with question-answer pairs. And then finally, in order to make it civilized, in order to prevent it from doing something funny, like giving a recipe of how to create a bomb or something, what they usually do is they do RL, where that the particular term that is given to it is RLHF, reinforcement learning with human feedback. So humans are sitting in front of the chatbot, they pose it a question, and if it is something that is not very good or doesn't sound good or is abusive or something, they provided a negative reward. And if it is something that is desirable, they provided a positive reward. So that's the third stage of training an LLM. So as you can see, it combines concepts from all of these categories in order to create a modern day LLM chatbot.
That's super cool.
Any questions so far?
Yeah, there's a couple of questions. Z, did you have a question?
Yeah. Thanks for taking the time to explain all of this. I still don't understand the concept of an agent. Why exactly it's necessary and how it does. How does it work? Like that's one thing I've always been a bit confused about.
Yeah. So reinforcement learning, although it's not my principal area of expertise, but I've been recently looking into it. So agent is, it's not like there are tons of different subtypes in reinforcement learning. So one example where they use deep learning inside reinforcement learning, which is called deep reinforcement learning. In that case, an agent could be a neural network. So you have, you can train that neural network to produce or to do an action, and you're not training it. You are just, you have a neural network, it does something, and if it is something that is desirable, you provide it a positive reward, and if it does something that is not desirable, you provide it a negative reward. Now, in that case, you are using the agent is a neural network. But sometimes there are types of reinforcement learning where you don't have an explicitly defined agent. So in that case, it is called model-free reinforcement learning, if I'm correct. In that case, what you do is that you define certain states in the environment. So let's say we have 4 different states: state 1, state 2, state 3, and state 4. In this case, if you say my current environment is in state 1, what is the next step that I should take or that I can take which would produce something that is desirable? So you only define what is called a Q table. So in a Q table, you just have different values for each state. So if you are in state S1 and you do take an action in a particular action state 1, the score that you get is 0.4. If you are in state 2, and the action that you do in state 2 gets you a score of 0.6. Now, initially, these Q values are at random, but gradually, over the training, you kind of refine these values in such a way that that in a particular state, the agent does an action which would yield a greater value of a greater Q value. Now, in this case, you don't have an explicit agent here. You just have these states and values assigned to those states, which kind of guides you how you should take an action. So this is another type of reinforcement learning. And if you see the taxonomy of reinforcement learning, there are like tons of different ways of doing this thing. But usually, like on a broader picture or a broader level, people usually do like explain it in this way, that you have an agent, an environment, it does some actions, and you do that. So yeah.
So there isn't like a specified way that agent has to update its memory when it gets a reward or not. That's left open to the implementation.
Yeah. So just like I said, like tons of different ways of doing it. One way of doing it would be using a neural network to predict what should be the next value.
Yeah.
Even in Q learning, there's a subtopic called deep Q learning. So in normal Q learning, they use what is called a Bellman's function, if I'm pronouncing this term correctly. So it's an equation which is kind of a recursive formula which tells you how you should refine these values. But since this Q learning assumes that the environment is categorized into these different states, every state is defined. But if you take this Q learning approach and try to solve a problem like self-driving car, it would be impossible for you to define every single different state, because there are just infinite things that car can do. So you cannot categorize that environment to certain predefined states. And in that way, you cannot use the direct Q learning approach using Bellman's equation. What you instead do is replace that with a neural network. Now, that neural network doesn't have to recognize every single state. It rather learns it directly by what action I should be doing if I am in a particular state. So they have then like omitted this Bellman's equation approach to do that. But again, the disclaimer is this is something that I'm not actively looking into. I've been recently doing some studies regarding it, so I'm not very confident in what I'm saying right now.
I see you've mentioned the use of chatbot during the reinforced learning, but I was recently working with IBM's chatbot for an event, but in that event, I was actually using it to the chatbot normally uses AI to pair the intents and then detect it, but as soon as it gets wrong or it doesn't know what intent to choose, then you could manually select that intent in order to train it. So next time you're gonna ask that question, it's gonna go where it's supposed to go. So you have to manually pair that up. In that case,
Yeah.
what would the agent be?
No, so like for chatbots,
Mm-hmm.
just like I said, it's not only the reinforcement learning that you are doing. For a chatbot, you do that the normal typical approach of first doing self-supervised learning, then fine-tuning it on question answers pairs in order to make it to make it a chatbot, like you're doing chatting with it. Because if you don't do that in the initial stage, you are just training it to predict next word. So it's just a generative model in that case.
Right.
This is a term given to it is the foundation models. So GPT-3 was a foundation model, which was just trained in SSL fashion to predict next word. Or the Llama models that you see, Llama 1, 2, or 3, these are the foundation models. Now, in order to make them a chatbot, you have to do the second step, which is the supervised learning by training it on question answer pairs. And then in order to align it to human behavior, or in order to prevent it from doing something crazy, you do the reinforcement learning thing with it. So you're not using agent in that case. This is just an approach that you manually foresee the output of what this chatbot is producing and then manually correcting it. Now, RLHF is just one approach. It's a very popular approach. Most of the time it is used, but even research is being done in order to automate that process as well. So now they are this feedback is also they are giving this task to another machine learning algorithm. The concept I think is called reinforcement learning with AI feedback, or another term that was given to it is constitutional AI. So they set a constitution where they define certain rules. This is what you can do. This is what you can do. And then based on that constitution, when you prompt an LLM to produce something, it has to be aligned to that constitution. So it cannot violate those rules as you have defined for it. It's a different
Right.
approach of doing it. And there are tons of others. Now, the specific concept that you talked about, it's also even available in ChatGPT, so that they provide, like, they randomly ask you when you prompt it, they answer it in two columns. So this is first approach, is second approach, and they ask you which one you prefer. And when you select one, that goes as a feedback, and they understand that this answer was more suitable for the user, and maybe they use it. Also, you can provide your feedback through other means as well, which would help them. And even if you don't provide it, you will see that in the beginning when you are using a chatbot, they print this message that we'll be using some of the chats to fine-tune our models. So don't put something that is
Confidential.
valuable
Yeah.
to you or confidential to you.
Mhm.
So multiple ways could be used in order to refine the output of these LLMs. Just like I said, James, we are doing machine learning 101 here, but because of the hot popularity of generative machine learning, everyone is interested in this. So I think we should be doing generative machine learning instead of machine learning 101 at this stage.
Maybe we can.
Yeah.
Yeah, we need
Anyways,
a separate workshop for that. Yeah. Yeah, that makes
yeah.
sense. Thank you.
Okay. So let me talk about a typical workflow of a normal machine learning project. So usually the whole story begins with the data itself. Now, how does that data comes into the availability? That's also something that is usually dealt with by web developers or maybe data engineers. So sometimes the data can come from live streams, APIs. Sometimes it is available in a database somewhere, but there could be multiple ways of ingesting this data. But usually the job of a machine learning engineer begins at this stage where you have the data available to you, so don't need to worry about how to gather this data. Sometimes you need to do web scraping to fetch the data from internet. And at that stage, the data is really messy. And that's why the second step after you get the data is what is called EDA, or elementary data analysis. So in EDA, what you do is normal visualizations using different Python packages or other packages you could use in order to get an insight of what this data looks like. So you are usually looking for any inconsistencies in the data, any missing entries, or anything that could be problematic. You visualize those things and you see what are the problematic areas. Once you do that, the next step is to fix those inconsistencies. So suppose you have some missing entries, obviously those need to be either removed or more clearly, they need to be imputed with something else. So if you have a column and you have some missing entries in it, what you can do is to replace those missing entries with the mean value of that column, or you can just simply provide it a constant value and replace all of them with it. So these kind of things are usually handled at the next stage, which is called pre-processing. Now, this is just one thing that you could do in the pre-processing, but of course, there are tons of other things that you can do. One other important thing that you can do is called feature engineering. So for traditional machine learning algorithms, you usually do handcrafted feature extraction, because traditional learning algorithms, as we'll see, they are not very powerful, or they're not very efficient in automatically extracting meaningful information or meaningful features from the data. So in order to make the job easy, what we do is we do handcrafted feature extraction, where we, just like James said, an example of combining length and width into area. That could be just an example of feature engineering. But on a more advanced level, you could, suppose you're working with some time series data, so you can transform the time series data into the frequency domain using Fourier analysis or something, and then you can use those as input features. So now you are doing handcrafted features extraction. You are not letting the algorithm decide what feature it should be looking for. You are rather doing that yourself in order to make its job easier. So feature extraction is also something that you do at this stage. And then certain algorithms require data to be in certain shape and format, so you also take care of those things here. And finally, there's what is called a trend to split that is usually done at this stage, where you set aside some of the data from the overall data, which you would be using in order to test the performance of the algorithm. So that's also something that is done here. The next stage is then model designing phase. So in the model designing, what you usually do if you are working with a neural network, because a neural network provides you a lot of customization abilities, so you can decide how many layers I want to use, how many neurons I want to use inside a layer, or all sorts of different architectures you can come up with. But even if you are doing traditional machine learning algorithms like support vector machines or other of the simpler models, in that stage, you can decide what nonlinearity function I want to use. Suppose you are doing SVM, what kernel function should I want to use? So those kind of decisions are usually handled at the model designing phase. Now, thankfully, there are tons of different Python packages which kind of makes it a lot more easier for us to do those things. You don't have to code things from scratch, but still, these are the choices that you have to make yourself in order to make this algorithm work better on your data. So that's model designing. Once the model is designed, the next step is then to train this model. So in model training, for instance, you're doing supervised learning, you're just simply providing those input-output pairs to the model, and you train the model. Now, how does training work? We'll see that maybe some other time, but in model training, once the model is trained, the next step is then to test the performance of this model, because you cannot just simply train the model and take it and deploy it into real world. You need to make sure it's working correctly. So you cannot deduce that from the training itself, because although it would work better on the training data, you'd see that the loss is reduced, the accuracy is increasing, but it's the data that it has seen during its training. So in order to make sure that it would work on unseen data, or it will generalize to wider applications, you need to have some way of testing it. And that's where the set-aside test data that I was talking about here comes into play. So you use that set-aside test data to test the performance of the model. And if the performance on the test data is good enough, you say that model would hopefully generalize well. And if it is not doing good on the test data, you come back to the model designing phase or come back to the pre-processing stage in order to do some alterations there, maybe pre-process data differently, maybe design the model differently in order to make it able to work correctly on the test data. So that's what happens in the evaluation, model evaluation phase. And then finally comes the deployment stage. So once you are satisfied from the performance of the model, you proceed towards deployment. And again, here, web developers like James comes into play, where you need to take that model and either present it as a web application or a mobile application in order to make use of it to do the things that it is intended to do. So this is a typical workflow of any machine learning problem. Of course, it would be different for different problems, but more or less it stays the same. And that's what most of the machine learning engineers work. Now, most of the time of the engineers is either spent on pre-processing. If your data is really messy, you need to take care of that. Or you would also spend quite some time in this phase where you would have to train the model. It wouldn't work correctly. You have to come back to the designing phase, again train it, again come back. So there's lots of back and forth movement at this stage as well when you are working with the ML problem. Any questions so far?
Hmm.
No, that makes sense. You can carry on.
Okay, so yeah, so the next step is then let's talk briefly about what comes on the algorithm side. So on the algorithm side, they're broadly categorized into two main categories. So one is called traditional learning algorithms, and then we have deep learning. Now, initially in the beginning phases of machine learning, there was no such division amongst the algorithms because a neural network was treated in the same way an SVM was treated or a decision tree was treated, because the compute power available at the time was not enough and data was not enough as well. So if you take a problem and if you try to solve it using a traditional machine learning algorithm, the performance would be equivalent to if you are using a neural network in order to solve that problem. But gradually over time, as data kept coming and as compute power kept increasing, the performance of neural networks tended to surpass way more than what the traditional machine learning algorithms were doing. So as you make the neural network bigger and bigger, and as the data that is available to it keeps coming bigger and bigger, at that stage, the performance of a neural network outshines the traditional learning algorithms. And there are even problems where it would be impossible for a traditional learning algorithm to solve it. So for instance, if we take object detection, there's no way you can take a traditional learning algorithm like SVM or anything to do object detection. These were only made possible by the deep learning. So back in 2013 or 14, even creating a cakes versus dogs classifier was a problem that was considered as the hard problem of computer vision. Nowadays, just a piece of cake for the models. So because of this exceptional performance of neural networks, they created this whole different field for these algorithms. They call it deep learning. The term deep comes from as you keep increasing the layers, and as you keep increasing the neurons in those layers, the model becomes bigger and bigger. In other words, it becomes deeper and deeper. So that's where the term deep learning comes from. On the traditional learning side, you have algorithms like, just like I said, SVM, support vector machine, linear regression, logistic regression, ensemble learning models like XGBoost, random forest, those kind of things. So this is what a typical division is between algorithms. So an examples of these would be these, and for deep learning, you have models such as normal feed-forward neural networks, you have convolutional neural networks, you have LSTMs, or more recently, you have transformers. All of these are models, deep learning models. Any questions?
I'm just trying to think about as deep learning has surpassed traditional learning in so many areas. Like, what are the areas where traditional machine learning would still be like preferable?
Yeah, so problems that are they are not considered too complex. So usually, like these days, most of the time when I see a traditional machine learning algorithm being used are areas where you have this nice looking tabular data, and you are either doing some regression on it, predicting a continuous value of something, or you are doing
Right.
classification on it, such as you have, let's say, customer on a website, you have customer data, and you are doing what next, like if you are deciding if this customer is, let's say, from this region or from that region, things like these, or other simpler tasks where you have this tabular data and the goal is to do regression classification. But complex problems like those in computer vision, so almost all of the problems in computer vision
Yeah.
are solved by deep learning these days. So you cannot take an SVM and make it solve object detection or image segmentation, or you cannot take an SVM to do text generation. So text generation or NLP is also an area where there's no way a traditional learning algorithm could beat the performance of modern deep learning algorithms. And then usually most of the time like if there's a problem which looks simpler, you just try how a traditional learning algorithm would work. But even for problems that seem fairly simple, usually don't usually traditional learning algorithms don't work there. So you can also use a neural network in that case as well. But there's a downside of using deep learning as well. If the problem is simple, maybe you don't have lots of data available to you. And just like I said, these algorithms usually, not usually, most of the time, their performance really become better when you have gigantic amounts of data. So if the data is limited, you usually don't do deep learning on it because it would just memorize all the data. Is a concept called overfitting in machine learning, where it performs really well on the training data, but doesn't generalize to test data. So if the data is limited, compute power is limited, and the problem is simple enough, the way to go is traditional learning algorithms. But if the problem is concept and there's room for compute and the data is heavy, then of course you do deep learning on it. Okay, so finally, let me just quickly introduce some of the Python packages that are used. So for the traditional learning side, usually the package that is used is sklearn. It was one of the older packages that were available. It's a really handy package, contains lots of tools for pre-processing as well, but almost all of the traditional learning algorithms are built into it, so you can use it for that. And then for deep learning side, you have TensorFlow or PyTorch that could be used for constructing neural networks. So these two are also used. And then for visualization purpose, you have Matplotlib and things like these, Seaborn. And then NumPy is also sometimes used for matrix multiplications. And of course, you have Pandas, which is used for taking care of tabular data. But of course, these are things where James would introduce you to and show you how they work. But these are just some of the packages that are used. Now, what we can do now is I start talking about the linear regression, or maybe we can postpone that to the next session. So I'd be looking into your comments.
Yeah, that's a good point. I think this probably took us about what 40 50 minutes to get through, 45 minutes to get through this. What did you guys think about this first part, like on it, how interesting it is? I say for myself, I find it very interesting, but I also find it I love coding, so I get a little restless because I know I can't.
Yeah, fair enough.
Code yet, which comes in the next lesson. What about you guys?
It's an interesting concept to grasp. Like you could get an idea from theory first and then implement it. So it makes sense to start off with that. So yeah, it's interesting. I enjoyed it.
Yeah, I thought it was really good, informative. Everyone has their own learning styles, so I think touching on all is also tricky but important. Like the only suggestion I had is in the video when you started like drawing like flowcharts and stuff, that was helpful. That's like literally the only way I learned. So having like maybe pre-drawn
Hmm.
uh, flowcharts into slides
Yeah.
is good, and then you can write on top of that. I felt that would keep otherwise you had on the one whiteboard too many things, and for someone who's like, let's say they just started reading about ML last week, it would be tricky to follow, purely because no, you explained it well, but it might be overwhelming.
Yeah, so actually, you're right. For the beginning session, because I was introducing lots of things, it would have been more nicer if I would have put them into the slides. But as you'll see, when we get into the algorithms part, there's not much stuff to write there. Like I'll be just writing a single formula, maybe talking about that. Or usually when I compute derivatives, um, it's usually more better if you do that on the board, uh, doing step by step. If you present all the steps at once and then just talk about it, some people also find that useful, but usually the math part is done in this way. So I'll see for the next session when we'll talk about the getting into the maths of, let's say, linear regression or something. If there's too much stuff there, I'd probably put it into slides. But if there's not too much, if it doesn't take me a lot of time writing it, maybe we'll stick to this writing style.
I really enjoyed this session. I enjoyed like the step-by-step progression of how we taught it, and I think I learned a lot. I even jotted some of the things down. I think I'm like just refreshing my memory and mentioning it. Thank you.
Cool. I think yeah, no, I think it was really cool. And probably it'll take us at least another hour to go through the linear regression. Well, yeah, maybe around an hour to go through linear regression and the code for asking all the questions we need to. So it's probably better to find a time to do that one next.
Yeah, so I'm okay with any case, but I think I think there was a lot of information in this one.
Yeah.
So in the next session we'll start with algorithms. Usually the way machine learning start is they begin the discussion with an algorithm and then try to take that algorithm, solve a problem, and the rest of the stuff goes with it. So things like data preprocessing, visualizations, all of those are covered over and over again for different algorithms, because different algorithms are used for different tasks, and each of the tasks would have its own requirement of doing preprocessing and stuff. So that is done with algorithms. So when you talk about linear regression, then James can tell you about how to preprocess the data and how to bring it into the shape or format that is acceptable to a linear regression algorithm.
Yeah, so much of the code is literally just reformatting and re-engineering the data.
Yeah.
Yeah, I do need to head for another meeting, but thanks for taking the time. This is really, I'm happy to provide like more feedback. This is super fun, and of course there's so much like trial and error and playing with different study methods and teaching methods. So
thanks for
congrats on getting this started.
Thanks for joining. The last thing I was just gonna throw in was you can leave if you have to, but I just wanted to ask what you guys think about these topics. Is there anything else that you actually want to see covered that's not on here?
Or maybe they can provide their feedback
Yeah.
later on. It's okay.
Sure. Yeah, think about it.
Yeah, I think it's a great start.
Okay, cool.
It's relevant.
Is this time generally good for people?
Yeah, it works for me.
Okay.
Yep.
Mhm.
Would you want to do like Tuesday?
Yeah,
That-
that would work as well, at least for me.
It works for me also.
Yeah, you good, Z?
Yeah, I'm okay
Yeah,
with
yeah.
the time as well.
Okay, sweet. All right, good. Let's do that. All right. Well,
Hey,
Yeah. thanks a lot.
see you guys later.
Thanks a lot, everyone. Cool. All right. I'm just ending the
Goodbye.
live stream. Yeah, cool. I just turned off the stream.